Select the best set of reagents to accomplish the following transformation. So if we take a look at the starting material, we see that we have an alkene. And if we look at the product, it appears that we've transformed both carbon atoms of the alkene into alcohol. So this is a diol. And specifically, they are pointing in opposite directions. So this product is a trans diol. So we need to think about how we can add two oxygens to this alkene and have them be on opposite sides to each other. So there is a key intermediate here, and that is an epoxide. So what we'd want to do is we want to take our alkene and transform it into an epoxide. And then if we do the SN2 attack on that epoxide, whatever nucleophile you're adding will come from opposite where this epoxide is, which is going to lead us to that trans diol. So the first thing we want to do is to take our alkene and make an epoxide. So we need a peroxy acid, something such as MCPBA. And then to open up this epoxide, this can be done under neutral conditions, it can be done under basic conditions or acidic conditions. And actually, knowing this MCPBA, this gives away our answer because we only have one option that actually involves the MCPBA, and we see that we're doing the ring opening under acidic conditions. So let's take a look at how that would occur. So if you've got your epoxide and you've got aqueous acid, the first thing that will take place is the acid-base reaction to protonate that epoxide, which is going to facilitate the ring opening reaction. And it does that because we are taking a relatively poor leaving group, which would be oxygen with a negative charge, and we're transforming it into something that can leave as a neutral group. So we have this protonated. And then we also have water. We have aqueous acid. So water is a nucleophile. And if it attacks one of these two carbon atoms of your epoxide, it actually doesn't matter which one. I decided to attack the bottom one just to be consistent with how we've drawn this trans diol. But technically you're getting both enantiomers of the product, so you wouldn't be wrong to show the attack from the top. But when this attacks, it's going to pop open the ring, and this is an SN2 step. And so this water is adding from the opposite face of where this epoxide was. And so this was on a wedge. This means this incoming water is on a dashed line. That's how we're getting this trans orientation. So we've broken this bond, so now we still have the wedge bond, and that center hasn't reacted, so that's why we keep it on wedge. And we have an OH, and we've added water from underneath, so this should be on a dash line. And really close to that trans diol product, we just need to remove that extra proton, and we have plenty of water around that can do that. So we can use water again to remove this proton, which will give us the trans diol. Okay, if we want to just look quickly at the other options, A is your conditions for ozonolysis. So this would actually cleave the alkene and give you two carbonyls. And both B and D are conditions that would give you the cis diol. Because in both of those cases, the two oxygens are added at the same time, so they end up on the same face of the alkene.